The first talk is a presentation of the paper A Theory of RPC Calculi for Client-Server Model, which extends existing stateless calculi to cover stateful interactions. The authors of the paper are Kwang-Hoon Choi and Byung-Mo Chang, and Kwang-Hoon will be presenting.
Hello everyone. I'd like to give a talk about a theory of RPC calculi for client-server model. My name is Kwang-Hoon Choi. This is a joint work with Byung-Mo Chang. Let me start with the background. Developing distributed systems is known as complex and error-prone. For example, consider a web system. You have to develop two programs, one for client and the other for server, generally in two different form languages. Also, the two programs need to be put together for testing and maintenance. Tier-less program languages, also called multi-tier form languages, can address this problem. You have only to develop a single tier-less program. Assuming a client-server model, the slicing compiler will automatically slice it into a client program and a server program. The communication between the two sliced programs will be automatically supported. Particularly, we are interested in a seamlessly tier-less program language for client-server model. It is basically a program language designed for a single computer, but naturally extended with the seamless RPC. By the seamless remote procedure call RPC, I mean that the remote procedure calls are language supported, bidirectional, and fully transparent. Lynx is a real-world seamlessly tier-less program language for a client-server model. An advantage of the seamlessly tier-less program language is this. If you look at this example program written in Lynx, you know that the tier-less program can be written exactly in the same way as writing single computer programs. The only difference is specifying the locational function. Here, client means that the main is a client function that must run at client. Here, server means that the authenticate is a server function that must run at server. Firstly, it is language supported, not library based. Second, you can call a server function from the client, and also you can call a client function from the server, so it is bidirectional. Third, the same syntax of Lambda application is used both for local procedure call and remote procedure call. No extra RPC keyword is used in the syntax. So, Lynx is a seamlessly tier-less program language for client-server model. The RPC calculus is a seamlessly tier-less calculus that extends the Lambda calculus with an RPC feature. It was proposed as a foundation of Lynx by Kufa and Wadler. In the calculus, C is the client location, S denotes the server location. Every Lambda abstraction has a location annotation, A, meaning that this must run at the specified location A. The RPC feature is described by the big step semantics. When you evaluate a Lambda application at location A, you evaluate the functional term L at the same location A into a Lambda abstraction with location annotation B. You also evaluate an argument M to a value W at the same location. And then, finally, you do beta reduction at the location B, not A. In the semantic rule for Lambda application, the caller location A and the function location is B. If A is different from B, then the Lambda application LM is a remote procedure call. If A is the same as B, it is a local procedure call. We use the same syntax for both calls, so it is fully transparent. The sim-list RPC is good for tier-list programming. However, due to the transparency of the sim-list RPC, every Lambda abstraction has to check the function location in runtime to decide if it is an RPC or not. This happens even in the sliced client and server programs after the slicing compilation. Our solution is to have located function types to track function location statically. Then we can statically decide if given Lambda application is a local procedure call or a remote procedure call. As a result, programmers can enjoy the advantage of the sim-list RPC in the tier-list programs, but no more runtime location checking is required in the sliced client and server programs. A key idea behind the typed RPC calculus is a location annotation on a function type. It is reminiscent of a location annotation on a Lambda abstraction. The located function type means that every Lambda abstraction of this type is guaranteed to run at the specified location A. For example, the argument f has a client function type because a client function is going to be bound to f. In the second example, f has neither a client function type nor a server function type because depending on the value of if conditioner, both client function and server function can be bound to f. In the typed RPC calculus, only monomorphic locations are allowed, so it is not well typed. The other key idea is that in the typed RPC calculus, you can identify all remote procedure calls statically in compile time. Let us see its typing rule. This is a refinement of the conventional Lambda application typing rule with respect to a caller location A and a function location B. Once your tier-list program is successfully type-checked, in every Lambda application LM, the caller location A and the function location B are fully analyzed and known in compile time. When caller location A is equal to the function location B, then that Lambda application is local procedure call. Otherwise, A is different from B, then this is a remote procedure call. In this way, you can statically decide if given Lambda application is local or remote procedure calls. By the type soundness property, every remote procedure call thus analyzed statically will never be dynamically changed into any local one. Thanks to this property, we can design a location information directed slicing compilation whose sliced client and server programs will never do location checking dynamically in runtime. This is an advantage over the untyped RPC calculus that always does location checking in the sliced client and server programs. The typed RPC calculus is good so far, but it has a problem because of using only monomorphic locations such as client and server, not something to refer to both. For example, you cannot write a single polymorphically located map function. Instead, you have to write a client map function and a server map function separately. A solution is to introduce polymorphic locations to the typed RPC calculus. It is proposed by a sequel research to the JFP paper about a polymorphic RPC calculus. This is joint work with James Cheney, Simon Fowler, and Sam Lindley. In the polymorphic RPC calculus, you can write a polymorphically located function with location abstraction over location variable and location application as you see in the slide. Then you have only to apply it to the client location to get a client map function. You can also apply it to the server location to get a server map function. This slide shows a comparison among the RPC calculi. To support the slicing compilation of the polymorphic RPC calculus, there are two approaches. One is a static approach that is described in the SQL paper. The other is a dynamic approach that we are currently working on. In this talk, I presented a theory of RPC calculi. There are potential applications of location types to other areas such as security and communication optimization. Also, we wanted to develop a fully fledged seamless tier-list functional form language based on the theory. Thank you for your attention.
Thanks, Kwang-Hoon. If you're watching the New York stream in Clowder, you should now see a Q&A link where I hope you can ask Kwang-Hoon questions by video chat.